Hello and welcome to your week 5 video for NUC 110. This week you're going to review the reactor water cleanup and the reactor recirculation system PowerPoints, and then watch the video here. And then I'm going to have you define around 10 or 11 terms, and then there's 2 videos down to watch at the bottom. So when you're defining these terms, please give me as much detail as possible. And I specifically want how it relates to the reactor. Venturi is a person, but we're talking about the Venturi effect, so it'll make a little bit more sense after you watch this particular video. And these 2 videos are fairly short just to help you with knowledge. So let's look at the reactor recirc system. So it provides a force I'm sorry. It provides a means to vary forced recirculation flow, and it controls reactor power. So it's basically how much water is in the actual core of the reactor at any given time. So how does it affect power? It actually sweeps away bubbles. So as the water goes up, it heats up more and more. And near the top of the fuel bundle, you'll actually have some bubbles as the water starts to boil. So if I push more water in with these recirculation pumps, it's going to actually push those bubbles up higher, which will actually cause power to go up because there's more water there to slow the neutrons down. That's sort of strange to think about, but it is the case. So the design basis. So whenever you see this is what the engineers were thinking about when they actually built the system. So they want to make sure that if there is a problem with the system, that we still are able to cover the fuel with water. So if some of the piping falls off, it's not going to affect the ability to reflood the reactor. It's going to have to stand up to reactor pressure because it's attached directly to the reactor, and it can remove all the heat that's in there and minimize maintenance because, of course, that system is going to be very close to the reactor. So the only time we can open it up is when the reactor is shut down. So if we have a problem with our recirc pumps, we're going to have to go in there in between outages, which means shutting the reactor down. So we've got total core flow, which is all the flow that's going through here. And then we have driving flow versus the driven flow. So reactor recirc is going to be the driving flow. It's a pump, and you can see it is not inside the reactor, right? Here's my reactor vessel. Here's the suction that's going off to recirc. Then it's a centrifugal pump that's over here, and that water is going to come back in to the inlet and go through our jet pumps up here. So that's the driven flow, is going to be the extra water from here, from this area, that's sucked down into the jet pump and ends up down here in the bottom. So the driving flow is what's coming through the reactor recirc pump, and the driven flow is that extra water that we're getting from the jet pump. And the two of them together are our total core flow. So here you go. You can see our pumps outside the reactor, and they're taking their suction here through a valve, goes through our pump and back up and into the reactor via the jet pumps. So this water just goes straight back into the jet pumps, and then we get that Venturi effect to pull extra water, the driven flow again. So here are some, whenever we're operating at 100% power, they're making about 3,000 megawatts thermal, but only around 1,000 megawatts electric because our machine is not 100% efficient. It's around 35, 36% efficient. So we are losing a lot of this heat to various things. The reactor is running at about 1030 psi-G, pounds per square inch on a gauge. And then you can see the flows here, right? These two flows better match up because the steam is the flow that's going out and the feed water is the flow that's coming in. So they need to match very, very closely. And you can see the recirc is actually about 3 times the water that's coming in. So for every unit of water that's coming in, it's going to make about 3 trips through the recirc system before it actually goes out. And then the jet pumps is doubling this again. So the reactor recirc is giving us about half, and the jet pumps are giving us a little bit more than the 35 million pounds mass per hour that we're getting from the recirc pumps. So that total core flow is 77 million pounds mass per hour. And the water comes in at around 430 degrees Fahrenheit, and it goes out around 550 degrees Fahrenheit as steam. So natural recirc, say that we're in an outage and we need to do some maintenance, we can get some natural recirculation going. So this water goes through the fuel, and as it does, it heats up and goes up, and it's going to displace the water that's up here, and that water is going to go get pushed down through the jet pumps and come back around. So that natural recirc, we can get about a third of the normal total core flow just by natural recirc. And you would only do that during an outage. That's not something you're going to do in a normal situation, but that's a huge amount of water to be moving around just from natural circ. But that's how much heat is actually being produced in here. And anything hot water, hot air, both going to rise, and they'll displace whatever's up here and make a nice little natural circulation loop there. So here is a problem. So we just talked about how whenever we were designing the system, we need to make sure that it doesn't need any maintenance. So we had a 50 micron filter, which is very, very small, and they were supposed to protect all the components inside the system. So the particulates that were smaller than that kept getting into our reactor recirc pumps and causing the seals to fail. So the reactor would have to shut down to go and replace these seals. So what they did instead is go to a much smaller filter, a 1 micron. So to try to keep all that crap out of the seals so that maybe we can run the whole 2 years without having to shut down to go in and replace the reactor recirc pump seals. And that has worked out pretty well so far for most of the plants that have done it. So here you can see the jet pumps. We've seen this picture before. So the recirc pump comes in these two. It splits into the two flows here, and it's going to go up. Oh, I apologize. I'm saying it backwards. It's going to come in the middle here and split off into two. And then there's a nozzle right here. And at the end of that nozzle, you're getting that Venturi effect. So the pressure gets very, very low right at the tip of the nozzle. And you can see this purple part is actually open. So down below this nozzle, is where the lowest pressure is, and everything hates this low pressure, so it's actually going to pull the water from all the surrounding area into the jet pump, and then it's going to go on its way into the reactor vessel. So there you go. This is a picture of the nozzle. As it comes together, you get this low pressure, and then all the water around it is going to get pulled in. And the driven flow is around 2/3 of the total flow. The driving flow is around 1/3. So, we're actually doing this work with our recirc pumps, producing about 1/3 of the flow. And as it gets here, it's going to pull this water in from the outside, and then it's going to come in and go underneath the reactor. So there are the different pieces and parts. If you are working as a reactor service technician, you'll become intimately familiar with these different parts. This is one of the things that they're going to have you looking at. You'll be dropping some cameras down into the reactor vessel and just taking a look at this. So how can a jet pump failure occur? This water is coming in with a lot of force. We just saw 35 million pounds mass per hour, which is a very large amount. Think about it, 35 million pounds of water passing through per hour. And as it hits right here on this underneath this hold down beam, it's forced to split into two directions. And then when it gets here, it's forced to split again. It's going 90 degrees. So these two 90-degree bends are two of the places where you're most likely to have a failure. So those are two places that are very, very important to look at whenever you're dropping a camera in there if you are an RST. So that ram's head is the weak point, kind of, just because the water has to make this big turn and it can cause problems. Another place would be the suction. If something gets inside there, any kind of foreign material, it can mess up the suction quite a bit. And then there's different joints that are connecting everything together that can also cause problems. So how are we going to control flow? So this is not something you need to know too in depth and in detail, but it's a variable frequency drive. So it's relatively hard to change a pump uh, in such a way as to change flow. So that is not an easy thing to do. So these big things, these are like the size of a school bus, are basically designed to give you a variable frequency and a variable current so that you can change the speed of those recirc pumps. So an easier way to do it, and why it's mostly done that way, is just to close a valve a little bit, close or open a valve a little bit, but we don't want to make a mistake and accidentally starve the water off our reactor. So we're controlling the AC motor, and we're taking a fixed AC voltage and frequency and turn them into a variable frequency and voltage. And that's all I'm going to go into with that. It's a really expensive machine to just basically be able to vary the speed on this relatively simple pump. Again, this thing is the size of a school bus, so that we can turn this dial I actually don't see the dial on here, but there's a small dial that changes the speed that the recirc pump is going to spin at. So all these different slides, you're going to see these interrelationships. And one of the questions I asked you was to define RBCCW. It's reactor building closed cooling water. So it's a loop of water that just runs around the reactor building and cools all the different systems. So you wouldn't be too surprised to see that there's also a TB CCW, a turbine building closed cooling water that cools all the systems there. And both of these are clean, fresh water. It's not salt water, but they do have a heat exchanger, and the heat exchanger is cooled by the salt water, and then that heat gets dumped off into the ocean or the air. So CRD is control rod drive. It's got an interrelationship. Air and nitrogen control tons and tons of different valves throughout the plant. It's got a relationship with reactor water cleanup and with RHR, which are two systems that we'll talk about later. So if we lose cooling to our pumps, then they're going to start to overheat. Within 10 minutes, you're going to have to shut that thing down because you're not cooling your heat anymore. So if you lose two systems, you got 90 seconds before these seals start to melt. They just get too hot, right? That reactor water is 500 degrees. So it's very, very hot and needs cooling almost constantly. Within 10 minutes, you're starting to damage things. So if there is a recirc system leak, so the pump seal starts to fail, right? And it's going to start to leak into the room that it's in. That's what the seal is doing. It's keeping the water in the pump instead of out on the floor. So if that seal starts to fail, that 1,000 pounds of reactor pressure is going to start to make its way into the dry well, which is the room that surrounds the entire reactor vessel and not a place that we go except during outages. So if this seal does start to leak, our flows are going to start to go down and our dry well temperature is going to start to go up, as well as our dry well leak detection. So we have some sumps down at the bottom, which is just a pit of water with a little pump in it. And if those sumps start to run a lot more, that means there's a lot more water in there, and there's a chance that water is coming from our recirc system. So our reactor is leaking at that point, and it becomes a very big deal. And you could also see a little mismatch, right? So we just said the feed water coming in and the steam going out better match pretty closely. So if they are not matched closely, then you're starting to see a problem here. So the water could be leaking from somewhere, and one of the culprits could be the recirc pump. So what's providing the motive force for the jet pumps? It's the recirc pumps. The Venturi effect is the fancy word for it, and that's one of the words you're going to define. So in a PWR, it's a little bit simpler because we're just water solid. So everywhere that you go, there's water, right? Everything in here has water. So there's just this reactor coolant pump that just takes the water once it's been cooled off in the steam generator and pumps it right back into the reactor. So there's 2 to 4 reactor coolant pumps, just depending on what kind of system we're looking at, who built the reactor and things like that. And there are the objectives. That's always a good review to look at for you all whenever you're done with this one. And then that video is included in your week 5 assignment. So that's it for this particular PowerPoint. So go ahead and take a break if you want to, and then we are going to jump into reactor water cleanup. So reactor water cleanup, you can see there's another video here, and that is the second video that you'll see in the assignment. And this reactor water cleanup, right, it is filtering out the reactor water. This is one of the nastiest things after the fuel that you're going to find in the reactor. So these filters get all the crap that leaks out from the reactor any way, shape, or form. It's going to leak out, and this reactor water cleanup is going to clean it up. So that's one of the places that you'll see this terrible sign: grave danger, very high radiation area. So it's a place that you absolutely should not go. If you ever see this sign, turn around and go the other way as quick as you can. So the purpose, right, is to keep that reactor water purity very, very high, because we don't want any corrosion to start to build up on our fuel or anywhere inside the reactor at all. So if that corrosion does start to build up, there's a chance that our fuel could start to rust. And it also is going to prevent heat transfer from occurring, because if we have a metal to water surface, that's going to be a really good way to transfer heat. But if it starts having debris build up on the outside of that metal, then it's not going to transfer heat nearly as well as it would otherwise. So here is a drawing of the system, and I think it does a little cartoon thing here. So we're taking the water from the recirc system, right? We're not taking it directly from the reactor. In a way we are, right? Because this is coming off the reactor. But We're taking it from here and it's going through the system over to some heat exchangers. I actually have 5 heat exchangers over here in a line. You'll remember whenever we talked about resin and demineralizers in one of the earlier chapters, we said that it melts at a high temperature. So this water coming off is around 500 degrees Fahrenheit, and it's coming off and it's going to go through 3 and then 2 heat exchangers. So these ones are regenerative, and these 2 are non-regenerative. So what regenerative means, it'll make a little bit more sense as we move on, but what's cooling this water is actually going to be heating back up on its way back towards the reactor. So these 2 are non-regenerative. So you can see RBCCW is what's cooling them. The reactor building closed cooling water is actually what's going to be cooling these off. And that heat is eventually just going to get dumped out into the ocean. So with these with these regenerative, that heat is going to get dumped back into the reactor. So that way we aren't losing as much efficiency, right? There's your reactor temperature, 532 degrees Fahrenheit. So after it goes through the heat exchangers, it's going to come around and go through a couple of pumps just to increase the pressure. And then after it does that, it's going to go through these 2 demineralizers. So we're just getting all the positive and negatively charged ions out of there. And then you can imagine like the sand or the pellets are also going to work as a filter. So if there's any larger debris in there, maybe something the size of a speck of rust, it's going to get stuck on these and not make its way back. So this is a physical filter as well as being an ion removal system. So there you can see it. That water has now, it's cool, right? It's blue, it's cooled off, and it's making its way through the pumps to increase the pressure, getting pushed through the demineralizers, and now it's going back through these regenerative heat exchangers. So it was 233 degrees Fahrenheit after here as it's going back, and now it's going to make its way back to the reactor at 430 degrees Fahrenheit. So as you can see, we're cooling this off a lot, right? It's getting down to 120 before it actually goes through here. So I believe the 230 is on the way down. So 230 Fahrenheit on the way down. And then on the way up here, it's getting back up to 430 degrees Fahrenheit. So there's a list of the major components, and we'll go through those one by one now. So the 2 pumps we just saw there are pumping around 280 gallons a minute, and they're redundant, so we only need one of them at a time. And it always tells you where the power is coming from. That's very important information. If you're an operator and this pump goes out, you want to know where to go to check the breaker and see if that is the problem. So the pumps will turn themselves off automatically. So you see this trip, just like a breaker tripping in your house. So if I close one of these valves, it's going to trip itself because it's not getting a suction. If the water starts getting too hot, it's just going to turn itself off again. And then if the system flow starts to go too far down, then it'll also turn itself off. Or if you turn it off, right? If you tell it to go off, it is going to turn itself off. That's what the pump looks like. So the motor is back here in the background, and here is our actual pump. And there is somebody standing in his little Homer Simpson suit trying to keep himself from getting contaminated. And this is a very, very ugly looking room because it's not worth the radiation for somebody to actually go in there and clean the room. And at one point, this particular plant went through and started changing those pumps out because over time they start to wear out, and they replaced them. So for Brunswick in particular, there's 3 of these regenerative heat exchangers. And again, they're very nasty radiation-wise. It's not something that you really want to go close to. And they're going to cool the water from 532 Fahrenheit down to around 233 degrees Fahrenheit. And on the way back, it's going to heat it back up to that 400 degrees Fahrenheit that we saw in the picture. After it goes through those, it's going to go through non-regenerative heat exchangers, and that's just going to dump the heat. Instead of back into the reactor, that heat is going to be dumped into RBCCW, and then from RBCCW, it'll get pushed into the salt water and out into the ocean. So that is what the heat exchangers look like, right? They just kind of look like a pipe, and you can see where the water's coming in, it's going to go down, and it's going to go out on the other end. So here is a good operational experience. So an unplanned radiation exposure because they were working on reactor water cleanup. These heat exchangers are nasty, and this person was in a field of almost 2,000 millirem per hour. So just to give you some context, the amount that you can get in a year is 5,000 millirem. So in a little bit over 5 hours, in a little bit over 2.5 hours, he was going to get his dose for the year. So a very, very nasty place to be. And his limit was, of course, we have limits, right? This is those procedural limits was 1,000 milligram per hour. So he almost doubled the amount that he was allowed to get. And then for the plant, the most that anybody could get anywhere was 1,500 milligram per hour. So he went above his limit, and he went above the entire plant's limit. And he was in there for 20 minutes altogether. It was really loud, but he had remote telemetry, so something basically like Bluetooth or Wi-Fi that would let people know outside. So his alarms, he couldn't hear them, and the people outside couldn't hear the alarms because the Wi-Fi wasn't going through the wall. You can imagine there's some pretty thick concrete walls to keep this amount of radiation away from the people that are outside. Well, he was inside the wall, and the signal couldn't pass through to the people on the outside to let him know. So make sure that people going in there know what they're doing, right? We're going to do a pre-job brief and a task preview and all that to make sure that he knows what's going on, and make sure there's good lighting in there as well. So sometimes the light bulbs go out. That's a room that we don't go into very often. And we want to keep our radiation exposure as low as reasonably achievable. That's that ALARA buzzword. So there's filters in there, and they each take about half the water that's going through. So both of those need to be running at the same time. You can go down to one for a little while while you're cleaning it off, but each one is going to be, then you're only going to be at half capacity. So this is not a system that is safety related. If this system goes off, we can continue to make electricity, but eventually, after a few days or a week or two, our chemistry is going to start to get bad, and then they might start talking about shutting down the plant. So this is not like something like the recirc pump. If one of those recirc pumps goes off, we need to get to 50% power immediately. The plant is going to take itself to 50% power whether or not you want to. So you better do it yourself. And typically, if one of the recirc pumps completely goes kaput, you're going to have to shut down and go in there and fix it. So with these, you have a little bit more time to actually you could take a week or two even to fix them in dire emergencies. So the filters are pre-coated with a mixture of cation and anion resin, just positive and negative resin. So here's 4 different modes for these filters, and we'll go through those one at a time. That's what the filter looks like. The media, the resin is going to be inside each of these tubes, and the resin is actually going to be held in there by a screen on the top and then by the water flow on the bottom. So if the water goes off, this resin is actually going to fall down. So we need to make sure the water never goes off, and we'll talk about that as we truck along here. So you can see the water's coming in, it's going through all those tubes we just saw that are full of resin, and then it's coming out the top. So if this water flow stops, there's nothing that preventing this resin from falling down. So in the hold mode, so this is just one little pump, and his whole job is to make sure that that flow never goes off. So if I turn off one of the main pumps, this little hold pump is going to kick itself on, and it's just going to push water in there all the time. It's just going to take the water, push it in the bottom, and just make sure that resin can't fall down. So that's his whole job in life, is to turn on when the other pump turns off for whatever reason, to hold the resin on there. So this is that defense in depth that we were talking about. We can't guarantee that we'll always have flow from those other pumps, so we have a one here that we can use to hold the resin on if we need to. So eventually, after a month or two, this resin starts to get bad. It's just not taking any of the ions out, and the chemistry guys are coming around. They check it every day. They check the reactor water chemistry, and they start seeing too much going on. So they're going to tell us to backwash the filter. So we're going to get that resin off, and we're going to put some new resin on. So as I said before, this stuff is very, very nasty after it's been in the exposed to the reactor water, because it's filtered out all the bad stuff. So we cannot go in there and physically do it ourselves. It's going to be behind a wall. So we're going to backwash it, which is just run water through there backwards. It's a fancy word for run water through backwards. We might blow some air in there too to try to loosen everything up and run some more water through. After we do that, we're going to coat it again. So we call it a pre-coat. So we're adding just a new layer of resin on there after it was cleaned off with that backwash cycle. So backwash and pre-coat, right? Backwash is washing all that other resin off, and pre-coat is putting new resin on. And then we talked about hold as well, which is just holding that resin in place until we get the system back up and running. So reactor water cleanup is attached to the recirc system. So it is in a way attached directly to the reactor. If something goes wrong with reactor water cleanup, there's a chance that it could be leaking water from the reactor into our reactor building, which is very bad. So if a reactor water level, RPV is reactor pressure vessel, if that water level starts to go down, we need to panic and we need to turn everything off that could be a leak. And like I said, reactor water cleanup is not safety related. So I can go ahead and shut this system down and isolate it. And then if the leak is coming from this system, I know that that's not this isn't the problem, right? I just isolated this if it is the problem. So if I have a delta flow, a change in flow, so 100 gallons are going in, but only 50 gallons are coming out, then again, I know I'm leaking 50 gallons a minute on the floor somewhere. If the room or the area start getting really hot, I know that reactor water is coming out and it's getting too hot. The same thing with all four of these. And then SLC is a system we'll talk about later. It's called standby liquid control. That's that one that injects boron in an emergency. So I don't really want to be cleaning up the reactor water if I'm to the point that I need boron. So I want to make sure that if reactor water cleanup comes on, or sorry, if SLC comes on, standby liquid control, and I start putting boron in, I don't want to be cleaning out that boron with this system. So you can see there's a lot of interrelationships here between different systems, and then we're always looking at these temperatures to see if I have hot water or steam leaking out from the reactor into my reactor building. So if you lose reactor water cleanup, it is not an emergency. It's a problem, but it is not an emergency, right? You're not going to melt down the reactor because reactor water cleanup went away. So, but you're going to start building up corrosion and crud on your fuel. So that is going to make the heat transfer worse, which could eventually, right after a month or two, if you kept running it with no water chemistry, it could cause fuel to melt because there's not as much heat removal. But in the short term, it's not going to be a huge problem. Another issue is you're going to start to get intergranular stress corrosion cracking. So cracking, we'll just stick with that, right? You're going to get small cracks in the stainless steel because where this corrosion starts to build up, it's going to weaken the metal a little bit. And so you want to keep reactor water cleanup in service as much as possible just to prevent any potential issues. So how is it related to the other systems? So we already talked a little bit about this. This is what's cooling my pumps, and it's also cooling the non-regenerative heat exchangers. You'll hear me talk about demineralized water. That's just the really clean water that we have, and we'll use that to backwash and pre-coat the filters. And then rad waste is the place where we send all that nasty resin after we get it out of those filters. So it'll sit over in rad waste for a few months, and then we will ship it off to South Carolina to be buried in a special nuclear landfill. So it's possible for the filter element to fail in there and for us to start having resin in the reactor. So this is not a good situation to be in. We don't want that resin in the reactor. You're going to start having weird chemistry if you have this resin in doing whatever it wants to do. And then that resin becomes foreign material and it could potentially damage components in the reactor. So now we're going to switch over to CVCS, which is the PWR equivalent. So it does all the things that we just talked about with reactor water cleanup, and it has a couple of more functions in a pressurized water reactor. So it's going to adjust the boric acid concentration. So we talked about this before, right? The PWR always has boron in the reactor, just slowing the reaction down. So the two ways that we control power in a boiling water reactor are the control rods and the water level, right? We just talked about that with the recirc pumps. If I turn recirc flow up, I'm going to push those bubbles up and I'm going to increase the power. So in a pressurized water reactor, I don't have that option, right? It's water solid all the time. So what I'm going to do instead is just dilute some boric acid and put it in there. So I can add some more boric acid, or I can dilute the boric acid that's in there by adding more pure water. So those are the two options that I have for controlling power with boric acid. The other way that they can do it is they have control rods, right? So both boiling and PWRs have control rods. But their secondary way to control power are very different. So here's a little drawing. We've got some pumps over here. We've got a tank. You can see the valves here. These are air controlled. This one is a motor controlled valve. And then I've got a little blender here. So as this water is coming from the boron tank, I'm going to be able to mix it together really well with the water before it goes into the reactor. So here you go. You can see the whole system. So here is the primary loop. I see my pressurizer and my steam generator, and I'm just taking a little bit of water off, and it's going through a regenerative heat exchanger. We've heard this one before, and then through a non-regenerative heat exchanger, through some demineralizers, and then it's going to go through a volume control tank. And then here we go, our chemical addition, if I need to add any other chemicals. And then there's my pure water tank and my boric acid tank. So I could use this in an emergency as well. If water level starts to go down for some reason over here, I've got a pure water tank right here ready to pump it into the reactor. But under normal circumstances, if you want power to go up, you're going to put in pure water. And if you want power to go down, you're going to put in the boric acid. So that's its extra job. And right, it's just getting pumped back in and going back into our, up this way and through the regenerative heat exchanger and then back into our primary loop here in our pressurized water reactor. So there's different types of ion exchangers. Most of the time now, you see this mixed bed, which is just the positives and the negatives are in there together, right? Cation and anion are our positives and negatives. And then in a PWR, they're going to have a deborating ion exchanger. So another way to get the boron out, as we're running the reactor down in the last few days, we need to get all that electricity we can out of it. So we'll turn on this deborating ion exchanger just to get the last little bit of iron out. The last little bit of boron out. There we go, to get the last shreds of power we can. So the volume control tank is just a reservoir to make up water as needed. So if the water the water's going to be leaking because these plants are old. The leaks are going to be relatively slow, and I'll just use this volume control tank to make any water up. So there is a larger schematic, and again, we'll get more into these over time, but you should start to see some pieces and parts that you know. So there's our deborating ion exchange. There's our mixed bed ion exchangers. And then down here is a cation bed if I need that for some other reason. You can see all the little valves as we're looking around here. Here's a temperature sensor and a pressure sensor. This one is a heat exchanger. So, and you can see it's going to closed cooling water. So, you know, that's the non-regenerative heat exchanger. And then a volume control tank. Here's another little heat exchanger. So a lot of things here that you should start being able to pick up on a little bit better. And as time rolls on, you'll learn more and more of these symbols. And then eventually you'll be able to make a lot more sense out of these drawings. So reactor water cleanup and CVCS are both clean and reactor coolant. They both have several heat exchangers. So there's only two on that particular drawing, but that's just for show. There are going to be more heat exchangers even in a pressurized water reactor. And you need to know the difference between the regenerative and non-regenerative heat exchangers. And CVCS has some extra job. It's going to borate the water, and the purpose for that is to control reactor power. So that's all I have for this week. Please let me know if you have any questions, and I hope you have a good week.